mixtures. All right. There are like two main types of matter, and one of them is a mixture. The other one is a pure substance, which you can see over here to the left, which is elements and compounds. We've been working with those all year. But now referring to mixtures, that's more than one substance, so like two or more, that are not chemically combined. So they're not a compound. For example, carbon dioxide is a compound, but if you have in the air, we have carbon dioxide, we have water vapor, we have nitrogen, we have oxygen. That's considered a mixture. None of those things are chemically combined, but they all exist in like the same sample, like in the same I don't know, place conditions. There are two types of mixtures. One is homogeneous. That's a solution where the substance is completely and evenly mixed. All of the molecules are evenly distributed. Something where we have like something that's been dissolved is a good example of that. So like a homogeneous mixture, like salt water, where we dissolve salt into water. Those salt particles are evenly distributed through those water molecules. So that would be a homogeneous solution. Heterogeneous has two. We have suspension and colloids, and the biggest difference between those is their particle size. Colloids tend to have a small particle size, while suspensions tend to have a big particle size. And the biggest difference is their speed of settling out. So colloids, they won't settle out immediately. Like you can't see it happening. Over time, you'll get separation. So for example, if you drink milk with fat in it and you leave it in your fridge and then you open your fridge, like leave it overnight or something for a long period of time. And then if you open your fridge really carefully and you take off the lid or open the container and you look in, there might be like a frothy layer at the top. That's because the fat separated out. It's not something that happens right away. So when you look at your milk, you don't see a separation happening, but it would happen over time. An example of a suspension would be like Italian salad dressing. That's something where if I use the Italian salad dressing, I take it out of the fridge and I shake it up and I pour it on my salad and I put it down, it immediately starts to separate. The oil immediately starts to go to the top. There's this layer of like water and herbs that kind of settle to the bottom. And if I were to set it on the table and then like my brother decided, 2 minutes later that he wanted Italian salad dressing too. So he picked it up. He would probably have to shake it again because all of everything had already separated out. However, if I took the milk out and shook it, got it all like mixed back up nice, and then poured it out, and then I set it down and my brother came, 2 minutes later to get some milk, he would not need to shake it. Kind of the same thing happens with ketchup, right? You leave ketchup for a long period of time and it gets like that oil layer at the top. So if I shake the ketchup and use it, whoever's using it after me doesn't have to shake it immediately. So that would be a colloid, and then the Italian salad dressing would be a suspension. So let's talk a little bit more about solutions, which are the homogeneous mixture. That's the one where everything is distributed. So 4 little tidbits of information. So first, it does not display the Tyndall effect. I'm going to talk about the Tyndall effect a little bit more on the next slide, but a solution would not display the Tyndall effect. A colloid and suspension would, which we'll see in a little bit, but again, a solution does not. You cannot filter a solution. So a solution means that you have a solute and a solvent. So you have something dissolved in something else. The solute is usually the smaller particles. The solvent is usually not particles, amount, like a smaller amount. Typically, it's like a solid or a gas, although you can dissolve liquid in a liquid. That is true. That is possible as well. But it's the one being dissolved, and then the solvent is the one doing the dissolving. But because it's a solution, that won't filter out. For example, when you have your saltwater mixture and you go to pour it through something like filter paper, you won't be able to collect the salt. The salt will pass through the same as the water does because it's been dissolved into its ions. 3, it does create an electrolytic solution. So electrolytic solutions mean that that electricity can easily flow because you are dissolving. When you have a solution, it's been dissolved. The ions that are in there can pass electricity through. Now, I want to make it clear, not all solutions are electrolytic. You can have a non-electrolytic solution, for example, air. There's no dissolving happening in air. Air is a bunch of molecules that are a mixture of these molecules. Dissolving didn't take place. So air could be an example of a non-electrolytic solution, which means that molecules or electricity could not flow. That's the difference between non-electrolytic, is there are no ions, therefore it won't let electricity flow. And then an electrolytic solution, it does allow electrons to flow, allowing electricity to pass through. Here's a nice little picture of the difference between heterogeneous and homogeneous. Homogeneous, you could see all the green and purple dots are evenly distributed, whereas heterogeneous, they're separated. So there's a nice little visual. This is the example of the Tyndall effect that I wanted to talk about. So in this very first vial, you can kind of see the red on the glass and then the red on the glass on the other side, but you don't see the red line in between. That's because that is a solution. It does not display the Tyndall effect. This line right here that you can see through these last two substances, it's coming out of a laser pointer, so that's light, and these are colloids or suspensions. I'm assuming, because I don't actually see two layers, they're probably both colloids. But they do display the Tyndall effect, and the Tyndall effect is the scattering of light. It means that the particles are large enough to scatter light. So here in the solution, they're not scattering light, but in these other two colloids, they are scattering light. Which is why we can see it. The light is still passing through the first one, we just can't see it because it's a solution. You kind of see this, I mean, if you've ever seen like a spy movie and somebody had to go through like a room that had a bunch of lasers in it, and they take like hairspray, that's what it looks like anyway, and they spray it in the air and then all the lines show up. That's the Tyndall effect. So the air is a solution. When you pass light through the air, you don't see little beams of light. If you have a laser pointer and you point it at the ceiling, you don't see the light from the laser pointer to the dot on the ceiling. But if I spray hairspray there, now all of a sudden you can see that beam of light, because the hairspray in the air will eventually fall out, right? If you put anything in the air, it's going to fall out. It's not just going to like float there, especially if it's a solid particle. So when you spray hairspray in the air, it falls to the ground, and because of that, it scatters the light. And actually, sometimes if your light is big enough, if you're using like a flashlight versus a laser pointer, and you spray something in the air and you shine the flashlight through it, you can actually see the little particles falling down to the ground. And it doesn't have to be hairspray. It could be, like a disinfectant, or whatever kind of spray you have in your house. Depending on which lab group you're part of, you might be displaying the Tyndall effect at home. So that will be really interesting and fun for you guys. All right, the next type, so those were solutions. The next type is our heterogeneous mixture. So we have a colloid, which I did talk about a little bit, but here it is in writing. So it will not separate by filtering because the particles are too small. However, it still will separate after a long period of time. Examples are ketchup, milk, gelatin. Those are all good examples for a colloid. It does display the Tyndall effect. Again, you can see it here. So here's pure water, which is a pure substance, right? It's a compound. It would not display the Tyndall effect. But here, because the particles are large enough, it will scatter the light, which means when the light hits the particle, it's going to bounce off in a different direction, and I'm going to be able to see it with my eyes. And that's what you see here in this picture of the Tyndall effect. Last is the suspension, the heterogeneous mixture, and this is the one that does separate quickly. So you will be able to separate it by filtering. Remember, with a colloid, those particles are too small, you can't, and then with a solution, you also can't. So the only one you can separate by filtration, gravity filtration, would be a suspension. Particles do settle out immediately. So here's an example of the Italian salad dressing. Once again, when you put it down, immediately those start to separate out. This happens with paint too. If you've ever, if you're a painter, or even if you've like painted your house, like the very first thing you have to do is mix the paint because it does separate out. It also does display the Tyndall effect. You can see here an example with the solution, the colloid, and the suspension. The colloid and suspension both have large enough particles to reflect light and display the Tyndall effect.